picture this. You have just spent, I don't know, maybe 6 months leading this team of totally brilliant engineers.
Oh, setting the scene. I like it.
Right. So you build this state-of-the-art deep learning model. The mathematics are just flawless.
Well, of course they are.
Yeah, and the hyperparameter tuning took weeks on, incredibly expensive compute. You finally deploy it to production, and you are just ready to revolutionize your company's revenue.
The dream of every ML engineer.
Exactly. But then, within 24 hours, the entire pipeline crashes. And it's not because the math was wrong.
It never is it?
No, it's because a downstream service changed a timestamp format from UTC to local time completely silently.
Oh, brutal.
Right. And suddenly your model started predicting the past instead of the future. So you've got millions of dollars on the line, and it's all halted by a simple data parsing error.
That is the harsh reality of machine learning in the wild, honestly.
It is brutal. It's totally unforgiving. And I think it requires a completely different mindset than just, knowing how to write PyTorch code in a Jupyter notebook.
I mean, it's a huge reality check. And I think it perfectly encapsulates why so many highly skilled data scientists just hit a complete brick wall when they step into the cloud engineering space.
Because they focus on the wrong things.
Yeah, basically. They optimize purely for the algorithm, right? But they completely ignore the scaffolding that's required to keep that algorithm alive and secure, cost-effective at a really massive scale.
Which brings us to our mission for this deep dive. You, the listener, are staring down the barrel of one of the most rigorous technical summits in the whole industry.
Which is becoming a Google Cloud Certified Professional Machine Learning Engineer. Or the PMLE, as we'll call it.
Exactly, the PMLE. And we actually have a highly detailed 45-slide internal strategic briefing labeled PMLE08 that basically maps out the exact expectations for this exam.
It is incredibly comprehensive.
It really is. But listen, we aren't here to just read you a syllabus, or give you a table of contents. That would be boring.
Very boring. And not particularly helpful for an exam this hard.
Right. We are going to deconstruct the actual architectural philosophy behind the exam. We're going to debate the trade-offs.
Because to pass this, you really have to stop thinking like a junior data scientist.
And start thinking like a senior cloud architect.
That distinction is literally everything. I mean, the PMLE does not care if you can derive the backpropagation algorithm on a whiteboard.
Right. They assume you already know the math.
Exactly. It assumes you know that.
Right.
What it tests is your engineering intuition. It tests your ability to look at a highly constrained business problem, factoring in things like latency, budget, and engineering hours, and then select the single most efficient path out of maybe 50 possible Google Cloud configurations.
So let's jump right into the deep end with the first major theme of the source material. And honestly, this part feels like a direct attack on the ego of every software engineer listening.
Oh, you're talking about the low-code stuff.
Yes. The blueprint heavily emphasizes architecting low-code ML solutions.
It really does. It's a huge pillar.
I mean, we're talking about using BigQuery ML to run linear classification, regression, time series forecasting, boosted trees.
All directly in the data warehouse.
Right. And defaulting to pre-trained ML APIs like vision or natural language translation, or even just utilizing auto ML.
It is an ego check, absolutely. For a lot of engineers, it feels like cheating, almost.
Yeah, and I want to push back on this aggressively, actually, because if a company is paying a top-tier salary for a professional machine learning engineer, and my solution to a complex classification problem is to just, write a 3-line SQL query in BigQuery instead of designing a custom neural network, aren't I basically just being lazy?
I totally get why it feels that way.
Right. Why is a rigorous engineering certification pushing me to take the bus when I clearly know how to build a high-performance sports car from scratch?
Well, I would argue that insisting on building the sports car when the business just needs to get across town is basically the definition of engineering immaturity.
Oh, okay.
I mean, think about the core philosophy of Google Cloud, right? And this is the metric by which this exam actually judges you. It's time to value.
Time to value. Okay, unpack that.
Basically, every single line of custom TensorFlow or PyTorch that you write is a liability.
Wait, really? A liability?
It is technical debt.
How is it a liability if I wrote it perfectly, though? Like, if my code is flawless?
Because code just doesn't exist in a vacuum, you know?
Yeah.
Custom code requires continuous testing. It requires dependency
Like
management.
dependency hell. Yeah.
Exactly. You have to containerize each, you have to provision infrastructure to serve it,
Mhm.
monitor the hardware utilization, and yeah, patch vulnerabilities in your framework versions constantly.
Okay, when you list it all out like that, it sounds exhausting.
It is.
Hmm.
So if you could achieve acceptable statistical accuracy using BigQuery ML, you have basically eliminated 90% of that operational overhead.
Okay, let's ground this in a practical scenario then. From the preparation material, we have this specific sample question, right? Question 45.
Oh, the tabular data one.
Right, so imagine you have these massive, structured tabular data sets, and they already live in BigQuery. The business comes to you and wants you to iterate rapidly.
So exploratory data analysis, feature selection, training, tuning, the whole 9 yards.
Exactly. And the constraint is doing this with minimal effort and ideally zero code outside of SQL.
A very common real-world scenario.
Now, a lot of engineers, myself included, probably would instinctively want to export that data, load it into a Pandas data frame in a Vertex AI Workbench notebook, and then run scikit-learn or train a custom model on Vertex.
And if you choose that path on the exam, you will absolutely fail the question.
Just flat out fail.
Flat out.
Mm-hmm.
Because let's look at the hidden costs of your instinct there. You want to pull data out of BigQuery into a notebook environment.
Right. Yeah, so I can play with it in Python.
Okay, well, first, there's the sheer latency of data movement. If we are talking about terabytes of tabular data, you are wasting hours, literally hours, just migrating data across the network.
Oh, true. Terabytes take a while.
Second, you are now duplicating storage. The data lives in BigQuery, and now it also lives in the block storage attached to your Vertex notebook.
Which means double the storage costs.
Exactly. And third, and this is a big one for enterprise, you've introduced a major security vulnerability.
Because the data left the warehouse.
Because the data has moved out of the governed, audited data warehouse environment and into some developer's local notebook storage.
Ah, right. Compliance teams would hate that, whereas BigQuery ML brings the compute directly to the storage.
Precisely. That's the magic of it. Under the hood, BigQuery operates on this distributed architecture called Dremel.
Right, Dremel.
So when you execute a create model statement in BigQuery ML, you are actually utilizing the massive parallel processing power of the existing BigQuery slots to train the model directly on the data right where it rests.
So there's literally zero data movement.
Zero data movement. There are absolutely no egress fees. You can handle the pre-processing, the training, and the inference purely through standard SQL.
Okay, so for structured tabular data where rapid iteration is the goal, choosing a custom Python environment over BigQuery ML is just a massive architectural mistake.
Exactly. It violates the constraint of minimal effort, and it introduces all those operational risks.
Okay, I concede the data movement argument for tabular data. That makes total sense. But let's look at unstructured data, like natural language.
Okay, let's do it.
So the material presents another scenario. This is question 53. An enterprise is expanding operations into Spain.
Right, the document translation scenario.
Yeah, so they have this massive backlog of standard business, legal, and financial documents. They need highly accurate translations quickly with the absolute least amount of engineering effort.
That phrase, least amount of engineering effort, is your golden clue.
Right. But the key constraint here is that these documents do not require complex, domain-specific jargon.
And that constraint is the linchpin of the entire architectural decision.
Okay, but hear me out. My first thought, wanting to ensure the highest possible accuracy, is to maybe extract sentences from these documents, pull them into a Vertex Workbench notebook, and train a custom AutoML text translation model.
Oh boy.
Or, even build a custom sequence-to-sequence model in TensorFlow if I really want total control over the embeddings. Why shouldn't I do that?
Because you are completely ignoring the least effort constraint, and frankly, you're overestimating the return on investment of custom training.
Okay, explain that.
Training a custom AutoML model requires curating a massive parallel corpus of English to Spanish translations just to feed the system.
Thousands and thousands of matched sentences.
Exactly. Do you have that data set ready?
Probably not.
Right. So if not, you have to buy it or you have to build it manually. Then you have to pay for the compute time to train the model, which could take hours or even days.
But surely the accuracy of a custom model would be better. I mean, custom is always better, right?
Only if the domain vocabulary is highly esoteric, like if it was super niche medical research. But the scenario explicitly stated that domain-specific jargon is not required.
Oh, right. It's just standard business Spanish.
Exactly. You are dealing with standard language. And the pre-trained Cloud Translation API already handles standard business Spanish with near human-level parity.
Okay, so you just hit the API endpoint and you're done.
Well, wait.
Wait, there's a catch. These are full business
Uh,
documents, PDFs, Word files, right?
exactly.
If I just send raw text to a standard API, I lose all the formatting.
Yes, you do.
I'd have to write custom scripts to parse the PDF, extract the text, send it, get the translation back, and then somehow rebuild the whole PDF layout from scratch.
That sounds like a massive amount of effort.
It is a massive amount of effort.
Yeah.
And it violates our core constraint again.
So what's the solution then?
And that is exactly where really deep, granular knowledge of the specific Google Cloud services is required for this exam. You don't just use the basic text translation endpoint.
Okay, what do you use? You use the document translation feature of the Cloud Translation API.
Document translation, is that a separate thing?
It's a specific feature within the service. It allows you to send the raw PDF or the docx file directly to the API, just as it is.
Oh, wow. And it keeps the formatting.
Yes. It translates the text in place
Yeah.
and returns a fully formatted document that looks visually identical to the original, just in a different language.
That is incredible.
Right. By choosing this specific service, you have reduced literally weeks of complex OCR, NLP, and document reconstruction engineering down to a single API call.
That is just a staggering reduction in technical debt. I mean, it really reinforces this idea that the best ML engineers often write the least amount of ML code.
That's the paradox of the job, yeah.
But I think this naturally leads us to a critical transition in the material.
Yeah.
We've talked about finding the fastest path to a prototype, or a quick solution, but a model on a laptop or a single API call in a test script is virtually useless to a global enterprise.
Completely useless.
Right, we have to scale it. We have to look at the engine room.
Which is where the PMLE exam really separates the theorists from the practitioners. And if you look at the source material, it reveals a very telling statistic.
Get me with it.
Roughly 21% of the entire exam is dedicated purely to automating pipelines and orchestration.
Wait, 21%. So 1 out of every 5 questions is just on plumbing.
Basically, yes.
Yeah.
Because plumbing is what keeps the system from collapsing.
I mean, I guess that makes sense.
It's MLOs, machine learning operations. It's the dominant reality of the actual job. You have to know how to evaluate hardware, design continuous integration and continuous delivery pipelines, scale serving endpoints, manage metadata, all of it.
Let's actually dissect the CI/CD aspect, because deploying an ML model feels significantly more complex than deploying a standard web application.
Oh, infinitely more complex.
Like in traditional software, you just compile the code, you push the binary, maybe run some unit tests, and you're good. But with ML, you have code, sure, but you also have data, and you have the model artifact itself. The material discusses utilizing Cloud Build to deploy Vertex AI pipelines.
Yes. Question 106 touches on this perfectly.
Right. So if I want to minimize the risk of breaking production, I obviously can't just have developers pushing code directly to the live endpoint.
Absolutely not. The exam rigorously tests your adherence to robust multi-stage deployment workflows.
Okay, so let's trace the architecture of a correct CI/CD pipeline in this context. Walk me through it.
Sure. So a developer commits new pipeline code, right? Let's say they updated the feature engineering logic in a kubeflow component.
Okay, so they push that to a repository like GitHub or Cloud Source repository.
Exactly. That commit automatically triggers Cloud Build.
So Cloud Build is acting as our orchestrator for the deployment itself.
Yes. Cloud Build spins up a clean, isolated environment. Its very first job is to build the source code and run unit tests.
Just standard software checks.
Right. It checks for syntax errors, missing dependencies, basic logic flaws in the Python code. If those tests pass, it compiles the pipeline into an executable artifact, like a JSON file.
Okay, and this is where I'd assume we just push that JSON to production Vertex AI, right?
And this is the critical juncture where people fail the exam.
Correct.
You do not deploy that artifact to production yet.
Oh, wait. Where does it go?
You push it to an artifact registry.
Artifact registry. Okay, so just storing the compiled version.
Yes, you store it there for version control and rollback capability. And then Cloud Build deploys that pipeline artifact to a completely isolated pre-production or staging environment within Vertex AI.
Why run the whole pipeline in staging, though? Like, if the unit tests pass, shouldn't we trust the code?
Because unit tests only prove that the code executes without crashing. They do not prove that the machine learning logic is actually sound.
Ah, I see.
Right. Running the pipeline in pre-production allows it to ingest staging data, train a candidate model, and then evaluate that model's performance metrics against a baseline.
So it's basically doing a dry run of the actual math.
Exactly. If the new pipeline logic generates a model with terrible precision, the pipeline fails safely in staging. No customers are impacted.
It's like an immune system for your production data. I absolutely love that.
That's a great way to put it. Only after a successful, validated run in the pre-production environment does the CI/CD system actually authorize the deployment of that validated pipeline structure to the production environment.
Okay, that makes perfect sense. So let's move from orchestrating the pipeline to actually serving the predictions at scale, because this is where costs can just spiral out of control instantly if you don't understand hardware architecture.
Oh, hardware choice is where you make or break a cloud budget.
Right. The material outlines this really brutal scenario. I think it's question 134. You have a scikit-learn classification model. It is deployed to an online endpoint in Vertex AI.
Okay, standard setup so far.
And you are expecting massive throughput. We are talking millions of requests per second, specifically concentrated during business hours like 8 a.m. to 7 p.m.
Okay, this is a classic capacity planning problem. It's totally designed to test your hardware intuition and your framework knowledge at the same time.
Well, millions of requests per second is an unbelievable load. So my immediate instinct, knowing that deep learning relies on GPU acceleration for massive parallel processing, is to just provision really heavy GPU nodes.
You want the big guns.
Right. I want to strap NVIDIA T4s or A100s to every single replica to make absolutely sure we don't bottleneck on compute.
And if you do that on the exam, you will bankrupt your project while simultaneously degrading your latency.
Wait, what? How does adding faster, more expensive hardware actually degrade performance?
Because you ignored the framework constraint.
The framework? You mean scikit-learn?
Yes. The scenario explicitly stated this is a scikit-learn classification model. Scikit-learn fundamentally is designed to run on CPUs.
Oh.
It does not possess native, out-of-the-box CUDA integration to leverage the parallel architecture of a GPU for inference.
So the framework literally physically cannot send the matrix multiplications to the GPU cores.
Exactly. The GPU just sits there, completely idling, consuming massive amounts of your budget, while the CPU on that machine struggles to handle 100% of the inference workload.
Wow. That is a massive trap.
The exam frequently sets this trap. You must map the hardware to the framework. Since it's scikit-learn, we absolutely must use standard CPU virtual machines.
Okay. So we ditch the GPUs, we go with CPUs. But one CPU virtual machine cannot handle millions of requests per second. It will hit a memory bottleneck, the request queue will overflow, and the endpoint will crash and just start returning 503 errors to the client.
Which is why you must configure aggressive horizontal scaling. The exam will give you options between setting a maximum replica count of 1 versus, say, 100.
But doesn't setting a max replica count of 100 mean I'm paying for 100 servers 24/7? My CFO would kill me?
No, and that's the absolute beauty of serverless auto-scaling endpoints in Vertex AI.
How does it actually work, cost-wise?
You define a minimum replica count, let's say perhaps 2 or 3, just to handle the baseline nighttime traffic and avoid cold starts.
Right, keep the lights on.
And then you set a maximum replica count of 100. You configure an auto-scaling metric based on, say, CPU utilization or requests per second.
Okay, so when that 8 a.m. spike hits.
When 8 a.m. hits and traffic surges, Vertex AI dynamically provisions dozens of identical CPU nodes automatically, distributing the millions of requests across them via an internal load balancer.
Incredible.
And then when 7 p.m. rolls around and traffic drops off, it automatically spins all those extra nodes down.
So you achieve massive throughput during peak hours, you minimize costs during off hours, and you don't waste a single cent on useless GPUs.
Exactly. That is the architectural mindset in a nutshell. It's not just about the model, it's about the physics and economics of the deployment.
I love that. But let's pivot, because even if you have the perfect low-code pipeline and the perfectly scaled CPU cluster, your system can still be a catastrophic failure if you misunderstand the data itself.
Oh, the data is everything.
Right, which brings us to the data dilemmas. Bias, skew, and data splits. Section 6 of the exam guide.
This is arguably the most dangerous minefield in machine learning. It is where models look absolutely flawless in the laboratory and completely collapse upon contact with the real world.
Yeah, so the material highlights a scenario involving a retail company, question 66. You have this historical tabular data containing sales figures from several existing stores. And crucially, every single row includes a sales timestamp.
Okay, timestamps are a huge red flag. Always pay attention to those.
Right, so the business wants you to train a model to predict future sales for a brand new store they are opening. When building your ML pipeline, you have to split this data set into training, validation, and testing sets.
Right, standard ML procedure. This question is testing your vigilance against data leakage.
Exactly. Now, standard practice, I mean, literally what you learn in day one of any data science bootcamp is to use a random split.
The classic 80-10-10.
Right. 80% for training, 10% validation, 10% testing. You shuffle the deck thoroughly to ensure the sets are statistically representative. Why is a standard random split a fatal error in this specific scenario?
Because of that sales timestamp. You are dealing with time series data. And time series data possesses a property called temporal autocorrelation.
Temporal autocorrelation. Basically meaning the sales on a Tuesday are highly correlated with the sales on a Monday.
Exactly. Buying behavior follows temporal trends.
Right.
Holidays, weekends, seasonality. Black Friday sales are related to the date.
Sure.
If you perform a random shuffle on time series data, you are inevitably going to place data from, say, December into your training set and data from November into your validation set.
So what? It's all just data.
So what? You have fundamentally broken the flow of time. You are training the model using future information to predict past events.
Oh, wow.
Right. The model will effortlessly memorize the seasonal trends from December, and when you ask it to validate its performance on November, it will look like a genius. Its accuracy metrics will be completely off the charts.
That's an illusion.
It is a total illusion, because when you deploy that model to production tomorrow, it will not have access to next month's data.
It can't see the future in real life.
Exactly. It'll be flying blind, and its performance will just plummet. This is classical future leakage. To prevent this, the exam requires you to know that for any data set with a temporal dependency, you absolutely must execute a chronological split.
Meaning you sort the data by the timestamp first.
Exactly. You train on the oldest data, let's say January through September.
Yeah.
You validate on October. You test on November.
So you force the model to learn how to predict the future based solely on the past.
Yes, which perfectly mirrors how it will be forced to operate in production.
That structural understanding of data is so critical. And it extends to how we evaluate the model's output, especially when the data is heavily skewed. There is a fascinating scenario, question 3, about a binary classification model designed to detect company logos in scanned documents.
Oh, this is a great one about metrics.
Yeah. The critical constraint here. 96% of the images in the training dataset do not contain a logo. It is a massive class imbalance.
This scenario is designed to test your immunity to the accuracy paradox.
The accuracy paradox. Okay, this is where high accuracy actually means your model is complete garbage, right?
Pretty much.
But I want to bypass the entry-level explanation of this. Like, we know that a dumb model that just guesses negative every single time will achieve 96% accuracy just because the data set is 96% empty.
Like, any beginner knows that.
And an engineer taking this exam obviously already knows what precision and recall are. What I really want to know is how this exam tests your ability to operationalize those metrics in Google Cloud when you are facing this exact kind of imbalance.
That's an excellent point. The exam totally assumes, the textbook definitions.
Yeah.
What it tests is your ability to optimize the model's behavior based on actual business risk.
Right.
So in a 96% imbalanced data set, if you look at overall accuracy as your guiding star, you are flying blind. The exam wants you to immediately pivot to evaluating the precision recall curve.
Okay, specifically utilizing the F1 score or the PRAUC, right? The area under the precision recall curve.
Exactly.
But why F1 over just maximizing recall? Like, if I'm looking for logos, shouldn't I just want the model to find every single logo, even if it makes a few mistakes along the way?
Well, because in an engineering context, false positives have a very real cost.
Okay, how so?
If you maximize recall by lowering your prediction threshold to near zero, your model's going to flag every single smudge or coffee stain or barcode on the paper as a logo.
Ah.
The downstream application, which is perhaps a human review team sitting in an office somewhere, will just be completely overwhelmed with garbage predictions. You'll waste all their time.
Right, and time is money.
Exactly. The F1 score is the harmonic mean of precision and recall. So by specifically optimizing for the F1 score in your hyperparameter tuning job on Vertex AI.
You're mathematically forcing the model to strike a balance.
Yes. You are forcing it to balance the penalty of missing a real logo against the operational cost of flagging a false one, while completely ignoring the massive volume of true negatives that inflate standard accuracy.
It's all about tuning the threshold to the specific business tolerance for error.
Perfectly said.
And I think this naturally leads into the ethical and fairness dimensions of data, which the exam heavily covers under responsible AI.
Hmm.
But again, let's look at this purely through an engineering and statistical lens, right?
Absolutely. That's how the exam frames it.
So there's a scenario, question 18, where you are building a targeted online advertising model, and you need to collect a data set from your live production traffic that does not reinforce unfair bias against specific demographic groups.
This is a classic pitfall. The trap here is assuming that random automatically equals fair.
How can random not be fair?
Well, if you just take a purely random sample of your production traffic, right? And let's say your current product happens to be overwhelmingly popular with one specific demographic.
Like maybe 80% of your users are from one specific geographic region?
Exactly. Your purely random training data will naturally just reflect that 80-20 skew.
And the neural network, which we know is fundamentally just a lazy optimization machine,
Very lazy.
it will learn that the absolute easiest way to minimize its loss function is to just memorize the preferences of that 80% majority and completely ignore the 20% minority.
Precisely. It will optimize for the majority class, degrading the experience for the minority class, which then causes them to churn and stop using the app, which makes your data even more skewed the next time you collect a random sample to train.
It is a vicious, self-reinforcing feedback loop.
It really is. So to engineer a solution to this, the exam expects you to bypass random sampling entirely and implement stratified sampling.
Stratified sampling. So that means you partition the production data into distinct demographic subgroups, the strata, and you intentionally sample from them such that the final training data set has a perfectly balanced representation.
Exactly. Regardless of how skewed the raw production traffic is, you ensure the training set is balanced.
You are forcing the data set to reflect the population you want to serve, not just the skewed population you currently have.
That's exactly the mindset.
But wait, what if you can't collect new data? There's another scenario, question 36, that posits your deployed model is underperforming on certain subgroups due to this class imbalance, but you are physically or legally unable to collect more samples, like maybe it's highly regulated healthcare data.
This is a tough one, but very common. This is where you have to manipulate the training process itself. You basically have two primary engineering levers here, upsampling and reweighting.
Okay, let's start with upsampling. I'm vaguely familiar with SMOT, the synthetic minority oversampling technique. Is that what we are talking about here?
It could be SEMOT, where you mathematically generate synthetic data points near the existing minority class points. Or it could be as simple as just literally duplicating the existing minority examples in the data set.
Just copying and pasting them.
Basically, yeah. By increasing the frequency of the underrepresented data, you force the badge gradient descent algorithm to encounter those examples more often, adjusting the weights to account for them.
But upsampling increases the physical size of the data set, which obviously increases training compute costs and time. So what about reweighting?
Reweighting is highly elegant because it doesn't change the data volume at all. It changes the mathematics of the loss function itself.
Oh, I like the sound of that. How?
You assign a class weight parameter to the minority subgroup. You are essentially telling the TensorFlow or PyTorch model, hey, if you make a prediction error on the majority class, the penalty is 1x. But if you make an error on the minority class, the penalty is 10x.
Oh, wow. So you make the minority class mathematically louder during backpropagation?
Exactly. The gradients shift much more aggressively when the model gets the minority class wrong, forcing the algorithm to find a decision boundary that accommodates them without requiring a single new row of data.
That is brilliant. Okay, so we have covered the low-code philosophy, the infrastructure of orchestration, and all these statistical traps of data. Now, I want to move to what I honestly consider the ultimate test of a cloud architect, the tool belt.
Yes, matching the exact service to the exact scenario.
Right. The PMLE exam is absolutely notorious for presenting hyper-specific constraints and demanding you select the exact right managed service. So I want to stress test these architectures right now.
Or maybe.
I'm going to present 4 complex scenarios derived directly from the exam material, and I want you to deconstruct the architectural logic for me. Rapid fire.
Bring them on. Let's do it.
Okay, scenario A, feature storage. Question 60. You are working for a massive global delivery company. You have millions of data points continuously streaming in, truck locations, parcel delivery statuses, real-time traffic conditions.
Okay, high-velocity streaming data.
You need a database to store these features. But here are the constraints. The serving infrastructure needs to retrieve these features with ultra-low latency for real-time online predictions.
Understood.
Concurrently, the data science team needs to query this exact same database to build training datasets, and they require historical data at a specific point in time to avoid the future leakage we discussed earlier.
Okay, so the immediate instinct for many data engineers hearing streaming data and ultra-low latency retrieval is to just immediately reach for Cloud Bigtable.
Yeah, Bigtable is Google's massive-scale, sub-millisecond NoSQL database. It powers search, it powers maps, it can absolutely handle the throughput of millions of delivery trucks. I would absolutely choose Bigtable here.
And if you choose Bigtable, you completely fail the architectural test.
Wait, really? Why?
Because you ignored the second constraint, the data scientist needing historical data at a specific point in time with minimal effort.
But wait, Bigtable stores timestamps with every single cell? I can definitely query historical data from it.
You can, technically, but you have to write the complex logic to do it safely. Let's say you were training a model to predict delivery times as of last Tuesday at 2 p.m. If you just query Bigtable directly, you might accidentally pull in a feature value that was updated on Wednesday.
Which instantly causes future data leakage into the training set.
Exactly. So to prevent this, your data engineering team has to write, test, and maintain incredibly complex point-in-time join logic to stitch the training data together correctly.
Which violates the implicit constraint of minimizing engineering overhead.
Precisely. Instead, the correct architectural choice here is the Vertex AI Feature Store.
Feature store, okay.
Feature Store is a managed service specifically designed for this exact dual workload paradigm. Under the hood, it actually uses a dual database architecture.
Oh, it's two databases.
Yeah. It uses a low-latency key-value store for the online serving to meet your real-time prediction needs. But for the offline training, it automatically synchronizes that data to BigQuery. And critically, Feature Store provides native API methods for point-in-time lookups out of the box.
So no custom logic.
None. When a data scientist requests a training data set as of last Tuesday at 2 p.m., the Feature Store automatically handles all the temporal joins, guaranteeing that no future data leaks into the training set.
You get the low latency of NoSQL and the temporal safety of a managed ML service. That is a masterclass in reading constraints.
You have to read every single word in these prompts.
Okay, scenario B, explainability and monitoring, question 125. You are at a major financial institution. You have developed a credit risk assessment model using a deep neural network trained on tabular financial data, so income, credit history, debt-to-income ratio.
Okay, neural net on tabular data.
Regulatory compliance legally requires you to explain exactly how much each feature contributed to a specific loan denial. Furthermore, once this model is deployed, you must monitor it for performance degradation over time.
Okay, two distinct problems.
Right. The options involve choosing between Vertex explainable AI methods, specifically sampled Shapley versus XRAI, and then choosing between monitoring for feature skew versus feature drift.
Let's divide and conquer this. First, explainability. You have a deep neural network, which is fundamentally a black box, and you need precise feature attribution. The exam offers XRAI and sampled Shapley.
Now, I know XRAI is incredibly powerful for neural networks.
It is very powerful, but XRAI is based on integrated gradients, and it is specifically optimized for image data.
Oh, image data.
Right. XRAI analyzes the pixels of an image and provides a visual heat map showing which specific regions of the image cause the neural network to make its classification, like highlighting the ears of a cat.
But our credit risk model isn't looking at pictures of applicants. It's looking at structured tabular data in columns.
Precisely. Applying XRAI to tabular data is the wrong architectural fit entirely. For tabular data, regardless of whether the underlying model is a tree ensemble or a complex neural network, sampled Shapley is the robust, correct choice.
Sampled Shapley, how does that work?
It is rooted in cooperative game theory, actually. It calculates the marginal contribution of each feature, say the applicant's income, by analyzing the model's predictions across random permutations of all the other features.
So it isolates the income's impact.
Yes, it gives you a mathematically rigorous, regulatory-compliant breakdown of exactly how much the income feature pushed the prediction toward a denial.
Okay, so sampled Shapley is locked in for the explainability part. Now, the monitoring constraint. We need to watch for degradation over time. Skew versus drift.
This tests your precise vocabulary regarding MLOps. Skew and drift are absolutely not synonyms, even though people use them that way.
What's the difference?
Training serving skew is an immediate discrepancy. It occurs the exact moment the model hits production. It usually means there is a fundamental mismatch in how the data is processed between the training environment and the serving environment.
Like if the training data normalized income between 0 and 1, but the live serving pipeline is accidentally feeding the model raw dollar amounts?
Exactly. The model will fail on the very first prediction. That is skew. Drift, however, is a slow decay. It happens over time because the statistical properties of the real world actually change.
Like macroeconomic factors shifting.
Right. The definition of a high-risk credit profile changes over 6 months due to inflation, for example.
Yeah.
Because the scenario explicitly stated monitoring for performance changes over time.
The correct MLOps architecture requires configuring Vertex AI model monitoring to detect feature distribution drift.
Bingo. Drift over time, skew in an instant.
Brilliant. Okay, scenario C, pushing the hardware limits. Question 124. You are tasked with pre-training a massive large language model on Google Cloud.
Okay, big compute budget.
Huge. Your training loop incorporates several highly specialized custom TensorFlow operations that your research team wrote in C++A. You are utilizing a very large batch size, and the primary constraint is minimizing total training time and compute costs. The decision comes down to utilizing a cluster of TPUs versus a cluster of GPUs using TensorFlow distribution strategies.
This is a fantastic trap. It is entirely designed to punish engineers who just blindly chase the fastest hardware on paper.
Which is exactly what I would do. My immediate reaction is TPU. Tensor processing units are Google's custom silicon designed specifically to accelerate massive matrix multiplications for deep learning.
They are beasts, yes.
Right. If I have an LLM and a massive batch size, a TPU pod will crush that workload faster than anything else in existence.
In a standard scenario, you would be 100% correct. A TPU pod utilizes a specialized high-speed interconnect architecture that allows massive synchronous training across thousands of chips with incredible efficiency. However,
Well, I missed a constraint, didn't I?
you missed the poison pill in the prompt.
The custom TensorFlow operations.
Yes, the custom C++ ops. TPUs execute code by compiling the TensorFlow graph using a specialized compiler called XLA, which stands for Accelerated Linear Algebra.
Okay, XLA.
XLA is absolutely brilliant at optimizing standard neural network operations, but it does not support every single arbitrary custom C++ operation you might decide to inject into TensorFlow.
Oh, no.
If your research team's custom ops cannot be compiled by XLA, the training job will hard crash on a TPU.
It literally won't run.
It will not run.
Mm-hmm.
Therefore, despite their raw speed, TPUs are the absolute wrong choice here due to software incompatibility. You must architect a GPU solution.
But a single GPU won't have enough memory for an LLM with a massive batch size. I'll get an out-of-memory error instantly.
Which is why you must leverage distributed training. You provision a cluster of high-end GPU virtual machines, perhaps utilizing A100s connected via NVLink, and you wrap your TensorFlow training king in a specific distribution strategy.
Which strategy?
To scale across multiple independent virtual machines, you use tf.distribute.multi-worker mirrored strategy.
Multi-worker mirrored strategy, that's a mouthful.
It is. But it creates copies of all your model variables on every single GPU across all workers. It uses a ring-all-reduce algorithm to synchronize the gradients efficiently across the network after every single batch.
So this satisfies all the constraints. It accommodates the custom ops because GPUs are vastly more flexible with custom C++ in, and it minimizes training time by horizontally scaling the compute.
That is exactly the level of architectural depth this exam demands. You have to know the hardware compilers.
Insane. Okay, final stress test. Scenario D. Unstructured data to structured insights. Question 85. A company has a massive archive of customer satisfaction surveys. These are physical paper forms that have been scanned and saved as PDFs.
Yep.
Crucially, every single form has the exact same layout. You need an automated pipeline to extract the text of the customer's comment and run sentiment analysis to predict overall satisfaction.
A classic computer vision and NLP pipeline problem.
Right. The two primary options presented are using the Cloud Vision API combined with the Natural Language API versus uptraining a document AI custom extractor and pairing it with the Natural Language API. Now, Vision API has incredible optical character recognition.
It does.
It can read text off a moving bus. Why wouldn't I just use Vision API to parse the PDFs?
because of the spatial constraints of the problem.
Hmm.
If you run a scanned paper form through the standard Vision API OCR, it will certainly extract all the text.
So what's the issue?
It returns that text as a massive unstructured block. It will read the header, the company logo text, the boilerplate instructions, the footers, and the actual customer comment, all jumbled together based on its own internal reading order heuristics.
Which means when I pass that massive, messy string of text to the natural language API for sentiment analysis, the NLP model is going to get completely confused by all the irrelevant boilerplate text.
Exactly. The signal-to-noise ratio is terrible. It might read a polite instruction header and think the customer is happy, but the golden clue in the prompt was, every single form has the exact same layout.
Ah, it's a highly structured document.
Yes, Document AI is purpose-built for this. By uptraining a Document AI custom extractor, you don't just extract text. You extract specific entities based on spatial bounding boxes.
So you literally draw a box around the comment section on the form and say, only read what is inside this exact box.
Yes, you provide a few dozen labeled examples to the Document AI model, teaching it the specific visual topology of your form.
Oh, that's so clean.
In production, the custom extractor completely ignores the headers, ignores the boilerplate, and surgically extracts only the string of text written inside the comment box.
You then pass that highly refined, clean string to the natural language API.
Right. And the sentiment analysis is vastly more accurate because you engineered a pipeline that isolates the signal and discards the noise from the very beginning.
Document AI for structured layouts. Vision API for unstructured images. Perfect. Okay, we've mapped out the technical depths of this exam, the low-code philosophy, orchestration, data integrity, and these incredibly complex architectures. As we close out this deep dive, let's talk about battle tactics.
The fun part.
The logistical reality of actually surviving this test. The PMLE is a 2-hour exam consisting of 50 to 60 multiple choice and multiple select questions.
The math on that is quite sobering when you break it down. You have roughly 2 to 2.4 minutes per question.
And as we've just demonstrated for the last hour, these are not flashcard questions. They are deeply complex architectural scenarios. If you are spending 5 minutes agonizing over the differences in TensorFlow distribution strategies, you are bleeding time.
You are failing the exam at that point.
But so how does a candidate actually manage this pressure?
The preparation material explicitly outlines a tactical approach. First, you have to read with absolute surgical precision. The difference between passing and failing often hinges on a single adjective in the prompt.
Like what?
If the prompt says most cost-effective, it instantly eliminates the highest performing hardware options like TPUs. If it says least operational overhead, it eliminates any answer involving custom coding or maintaining your own infrastructure. You must identify the primary constraint instantly.
And what happens when you encounter a scenario that completely paralyzes you? Like you just blank.
You mark it for review and you move on immediately.
Don't fight it.
This is a critical psychological tactic. The exam interface allows you to flag questions. Do not let your ego force you to try and solve a problem that is just eating your clock.
Right, because every minute you waste is a minute you steal from an easy question later on.
Exactly. Let your subconscious process the complex scenario in the background while you knock out 3 or 4 questions that you know instantly.
And always guess if you have to, right? Never leave it blank.
Absolutely always guess. There is no negative marking for incorrect answers. A blank answer guarantees 0 points. Even if you have to guess, you can usually eliminate 2 blatantly incorrect architectural choices, like using a TPU for incompatible custom ops, turning a 25% chance into a 50% coin flip.
50-50 is better than 0. Now, logistically, candidates have to choose their testing environment. Online proctored or on-site at a physical testing center.
This is a highly personal choice, but you absolutely must know the constraints of each before you book. Online proctoring is very convenient, but the security protocols are, honestly, draconian.
How bad is it?
You must install a secure browser that completely locks down your operating system. You are restricted to a single monitor, no dual-screen setups allowed.
Oh, that's annoying for developers.
Very. Your desk must be completely barren. No papers, no pens, no water glasses with labels on them, no wearable electronics at all. Your webcam and microphone must remain active, and you must stay in the camera frame the entire time. No leaning out to stretch.
Okay, so if the thought of a remote proctor scrutinizing your every eye movement stresses you out, on-site is the alternative.
Yeah, with on-site, you trade environmental control for mental simplicity. You arrive 15 minutes early, hand over your identification, lock your phone and smartwatch in a provided locker, and sit at their lockdown terminal. The environmental stress is entirely offloaded to the testing center staff.
And before you even book that ticket, the source material offers a really fantastic piece of advice for preparation, which is the Google Cloud Arcade.
Oh, I highly, highly recommend this.
What is it?
Reading documentation and listening to deep dives is vital for architectural theory, obviously. But cloud engineering is a contact sport.
You have to actually touch the buttons.
Yes, the Google Cloud Arcade provides gamified, hands-on labs in actual live Google Cloud environments at no cost to you. You earn digital badges, but more importantly, you build actual muscle memory.
So you actually experience the pain of a cloud build pipeline failing or the satisfaction of seeing an auto-scaling endpoint spin up in real time.
Exactly. When you face a question on the exam about Vertex AI deployment architectures, you aren't just recalling a diagram you saw in a PDF, you are recalling a system you actually built and broke and debugged yourself.
That experiential knowledge is priceless. So we've covered the entire blueprint of PMLE08. If we synthesize everything we've debated today, what is the core identity of the engineer who actually passes this exam?
I would say the candidate who passes is fundamentally an architect of trade-offs.
An architect of trade-offs.
Yes, they have evolved past the junior desire to write custom code for every single problem. They ruthlessly prioritize time to value, utilizing managed services and APIs whenever it's statistically acceptable.
They view manual processes as systemic failures.
Right, opting to orchestrate and automate resilient CI/CD pipelines instead. They respect the physics of scale, matching frameworks to hardware efficiently to save money. And they possess a deep, almost paranoid vigilance regarding data integrity, constantly monitoring for leakage, skew, drift, and imbalance.
They build resilient, scalable systems that actually deliver business value rather than just cool local experiments on their laptops.
Exactly.
And I think that brings us to the final thought we want to leave you with. This certification, the PMLE, it tests your mastery of today's specific tools. BigQuery ML, Vertex AI, TPU clusters, feature store. But tools are ephemeral.
They change constantly.
Right. In 5 years, the managed services will be different, the hardware will be exponentially faster, and the APIs will probably be unrecognizable. But the mindset you are forging right now by studying for this exam,
The rigorous mindset.
the relentless evaluation of latency, cost, scale, and operational overhead, that architectural mindset is permanent. It is exactly what will prepare you to engineer the AI systems of 2030, systems that haven't even been conceptualized yet.
It's a foundation for the future.
So as you prepare to tackle this summit, ask yourself this. When the tools inevitably change, but the core human business problems remain exactly the same, what will your very first architectural decision be?